Hello and welcome to another Common Core Geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson number 6 on Parallel Line Properties Review. Wow, that is a mouthful. Now, the reason that I want to review some of the major properties about parallel lines is that we're going to need them in proofs coming up very soon. This lesson will seek to review those parallel line properties. We'll maybe even use them to do a little bit of proof, but mainly we'll be just solving problems with the properties. Ooh, mouthful. Anyway, let's get right into it. All right, exercise number 1. Let's jump in and take a look. In the following diagram, lines M and N are parallel and are cut by transversal line R. Angles have been numbered to make identifying them easier. All right? Now, we talked about this in a previous lesson. Whenever you have two lines, they don't even have to be parallel, and they're intersected by a third line known as a transversal. 8 separate angles are created. 1, 2, 3, 4, 5, 6, 7, 8. It's easy enough, right? 8 angles are created. Some of those angles are known as corresponding angles. Some of them are known as alternate interior angles. There's also angles called same-side interior angles, same-side exterior angles, all sorts of different names. But the two most important ones are corresponding angles and alternate interior angles. And that's what this first exercise gets at. So let's look at letter A. Give all corresponding angle pairs what is true about their measures. All right? See if you can remember what the corresponding angle pairs are. Are you ready to go through them? Let's do it. Again, the idea of corresponding angle pairs are angles that are in the same place on the x, so to speak. In other words, angle 1 here corresponds with angle 6 here, because they're in the sort of upper left-hand portion of the t or the x. So angle 1 and angle 6 correspond, right? Angle 3 and angle 5 correspond, these two. Angle 7 and angle 2 and angle 4 and angle 8. All right, I'm going to just kind of erase these really quick. Okay. What's true about the measure of corresponding angles? Well, let's just take a look at angle 2. Remember, angle 2 corresponds to angle 7. And watch what happens when I move angle 2, right? Here's the size of that angle. When I move it up to the 7 position, right, those two angles coincide, right, when I translate that angle up, which means their measures are equal. Or you could say that the angles are congruent. Again, take a look at how nice that is, right? We've got angle 2 translated up, and we're sitting on top of angle 7. You can always kind of prove from a transformation perspective that corresponding angles are congruent using a simple translation. Again, that was back in Unit 2, so we're not going to go there right now. Let's take a look at exercise B, 1B. Give all alternate interior angle pairs. Alternate interior angle pairs. What's true about their measures? All right, so see if you can name the two, because there's only 2 of them, alternate interior angle pairs. All right, let's take a look. Alternate interior angles, undoubtedly the most important of pairs of angles created by parallel lines. One pair is 5 and 2. Okay, so angle 5 and angle 2, right? And the other pair is 1 and 8. Angle 1 and angle 8. And if you really think about it, the terminology is exactly correct. All right? They're alternate because they're on alternate sides of the transversal, and they're interior because they're on the inside of the two lines. Alternate, opposite sides, interior on the inside. Now, what's true about their measures? Well, let's take a look again at angle 2. Remember, angle 2 is alternate interior with angle 5. And if I take angle 2 and I rotate it by 180 degrees about the midpoint of this line segment, then what I see is that it perfectly matches up with angle 5. So yet again, they are congruent, right? Alternate interior angle pairs are congruent, or they have equal measures. Again, one of the cool things is from a transformation perspective, you can always prove that alternate interior angle pairs are congruent. Let me get rid of that little mark. You can always prove they're congruent by a 180-degree rotation about the midpoint of this line segment. All right, but again, that's from a transformation perspective. So now what we want to do is we want to use these two types of angle pairs to solve some problems and do some proofs. All right, so let's get into it. Exercise number 2. In the diagram below, R is parallel to S and are cut by transversal M. Explain why the measure of angle 1 must be equal to 47 degrees. All right. Now it's kind of interesting because a lot of times we might just be asked to figure out what the value of the measure of angle 1 is. Here we're asked to explain why the measure of angle 1 has to be 47 degrees. All right. So what I'd like you to do is pause the video right now and think about how you would explain that the measure of angle 1 is equal to 47 degrees. Take a little bit of time. All right, I say we go through it. Okay, now, it is never problematic, maybe I shouldn't say never, but it's almost never problematic to add things to a diagram, especially the numbering of angles. We'll do that a lot in this course, okay? So I'm going to say that that is angle 2, okay? I'm going to say that's angle 2. Now, one thing that I know is that the measure of angle 2 plus 133 degrees must be 180 degrees because these two form a straight angle, right? These two form a straight angle, and straight angles always measure 180 degrees. But now it's very easy then to solve this equation by subtracting 133 degrees from both sides, and we find that the measure of angle 2 is equal to 47 degrees. All right, that's simple, okay? But the problem asked me to explain why the measure of angle 1 was 47 degrees. Well, I can now say that angle 1 and angle 2 are corresponding angles. Right? They're not alternate interior angles, but they're corresponding angles created by parallel lines. That's key. You see, if I don't know that those two lines are parallel, then my entire analysis just falls apart. You got to watch out. Sometimes, especially on tests like the SAT, they'll kind of try to trick you or play around with you a little bit on that, all right? So be careful with that. But right now I can say angle 1 and angle 2 are corresponding angles created by parallel lines, so they must be congruent. All right? And that really ends our explanation, right? I was asked to explain why the measure of angle 1 was 47 degrees. I can establish that the measure of angle 2 is 47 degrees just simply because 2 and that 133 have to sum up to be 180. And then because I've got parallel lines cut by a transversal, 2 and 1 are corresponding angles that have to be congruent. All right, there it is. Take a moment if you need to and write down any of this, and then we'll move on to another parallel line problem. All right, let's keep going. Exercise number 3. In the diagram shown, EF is parallel to DC. Measure of angle ABC is 112 degrees, and measure of angle EAD is 24 degrees. Which of the following represents the measure of angle DAB? All right, great. So what I'd like you to do is take a few moments. I've highlighted some angles in my diagram, and we'll eventually get to why I did that. But I'd like you to take a few moments and see if you can figure out the correct multiple choice answer to this problem. All right, let's go through it. Now, one thing that's really, really important is that you're able to properly identify the angles that they're talking about. So let's mark it up on our diagram. We're told that the measure of angle ABC is 112 degrees. That's this angle right here. And the measure of angle EAD is 24 degrees. That's this angle right in here. And we want the measure of angle DAB. That would be this angle right in here. All right? So that's the one that I'm looking for. Now, how do I find it? Well, the key here is that the measure of angle ABC, right? Maybe I'll write this down. The measure of angle ABC must be equal to the measure of angle EAB. Let's make sure we know which one EAB is, right? That's this angle right here. Okay? And again, you can see that pretty easily. They're alternate interior angles. That one just sort of rotates right up like that. Okay? Rotates right on top of it. Right? Down here 112, up here 112. Now, because of that, we can use the concept of the whole as the sum of its parts. No proof here, no proof. We're just using that idea to say, well, this whole angle must be 112 degrees. So the one I'm now looking for, the measure of angle DAB, and no, I won't dab for you, is 112 degrees minus 24 degrees, which is 92 is 88 degrees for choice 3. Right? I had to just do the subtraction in my head. I always have to be careful for that. My Achilles heel in terms of the 4 basic functions is subtraction. We all have our weaknesses. Mine are many. Anyway, so it's a simple enough problem, but you have to understand the idea of alternate interior angles, the angles of the Z, so to speak, being congruent, and you have to be able to identify which angle is which. Very, very critical. All right, let's move on to the next problem. Take a look at what we have here. We're going to do a little bit of a proof now. Lots of proof in this unit. Exercise number 4. In the following diagrams, lines, really should just say diagram, there's only one, lines M and N are parallel and cut by straight line transversal R. Angles are numbered, lots of typos in this one, numbered as shown, all right? We want to prove that 1 and 3 are supplementary. Now, this is actually kind of an important proof. It's not necessarily a very difficult proof, but it's an important proof. One of the things that's very useful to know, right? We've talked about corresponding angles. We've talked about alternate interior angles, right? But another piece of terminology that's kind of nice is when you have 2 angles that are on the same side of the transversal, like these 2, and are on the inside of the parallel lines, okay? Same side interior angles. Those angles will be supplementary. They will add up to 180 degrees. We'll want that when we talk about parallelograms in the next unit, all right? These 2 angles will always add up to 180, and we're going to prove it right now. Now, let's think about how that's done. Pause the video now and take a few moments to think about how you can establish that 1 and 3 will add up to 180 degrees. Let's go through it. Okay, so, almost there we go. There's my statements and reasons. Well, obviously, we got to start with our givens. Line M is parallel to line N, given. Now, what do we know from that? Well, we know immediately from that angle 1 is congruent to angle 2. Okay, I'm going to erase angle 3 for right now. We know that angle 1 is congruent to angle 2. Now, be careful. It would be tempting to write down as the reason for this the definition of alternate interior angles. Except that's not the definition of alternate interior angles. Right? Alternate interior angles are just two angles that are on either side of a transversal that's cut across two random lines. They don't even have to be parallel lines. All right? Unfortunately, the wording here is kind of lengthy and a little bit obnoxious, which is alternate interior angles formed by parallel lines are congruent. All right? Maybe I should even get deeper into it. Alternate interior angles created when two parallel lines are crossed by a transversal are congruent. Okay? The point is that you need to establish the fact that they're alternate interior angles and that there's parallel lines involved in order to get 1 and 2 to be congruent. So 1 and 2 are congruent. But ultimately, it's not what I'm trying to prove. I'm trying to prove 1 and 3 add up to 180 degrees. Well, I got to get that 180 in somehow. So here it comes. The measure of angle 2 plus the measure of angle 3, these two angles, have to sum to be 180. What's my reason for that? Angles that form a straight angle are supplementary, right? These two angles add to be 180 degrees because they form a straight angle. Great. And you can probably see how we're now going to finish this, right? I really want 1 and 3 adding to 180. But I know 1 and 2 are congruent. So I can simply say the measure of 1 plus the measure of 3 is 180. And what did I really do? All I really did was I took the measure of angle 2, or really just angle 2, and I replaced it with angle 1. That is the substitution property. Anytime two things are either congruent to each other or equal to each other, you can substitute one for the other at any time you want. That's called substitution. You did it a lot in algebra. All right, you do it all the time in algebra. Now, we're basically there. One might even think we're done, okay? Except ultimately, we pretty much always want to end a proof with whatever they're telling me to prove, right? i.e., prove that angle 1 and angle 3 are supplementary, so angle 1 and angle 3 are supplementary. Why? Because the definition of supplementary angles. Now, you could say something like, well, when two angles add up to 180 degrees, we call them supplementary. All right, but this is one of those times when I really think it's very, very appropriate to use definition of. Literally, what supplementary angles are two angles that add up to 180. So if I've got two angles that add up to 180, like 1 and 3, well, then they are supplementary because it fits the definition of supplementary angles. All right, great. Let me step out of the way, give you a moment to copy down anything you might need to, and then we'll move on with parallel line problems. All right, good enough? Let's move on. Okay. Now, the last little piece that we're going to do today is we are going to prove one of the most important ideas in all of geometry, and one of the ones that is known the best in geometry, right? What is true about the sum of the three angles of a triangle always? Think about this for a moment. Well, I hope you already know the answer, right? But let's take a look at this GeoGebra widget, okay? And see if we can kind of figure it out. Now, in this GeoGebra widget, what I've got is I've got a triangle, kind of a random triangle. And I've got the three angles, okay? Now it's a little bit tricky because these are all kind of rounded to the nearest hundredth, all right? But if I were to add up the three measures of these angles, no matter where I put them whatsoever, what I would find is one of the most famous facts in all of mathematics. And that's that the sum is always 180 degrees. always. Now, keep in mind, this isn't the side lengths of a triangle. That's one of the larger misconceptions about geometry, is that somehow if I add up the lengths of the sides of a triangle, I'll get 180. 180 what? You know what I mean? I can have a triangle that's got a perimeter of 3 feet. I can have a triangle that has a perimeter of 75 miles, right? It's that these angles add up to be 180 always. But why? You can experiment with it in previous courses, but in this course, we're going to prove it. And the last exercise today, specifically, is going to prove that the sum of the angles, the 3 angles of a triangle, is always 180. Let's do it. All right. I love this proof. I've even seen this proof, strangely enough, come up on a standardized exam before. So let's take a look at it, okay? Exercise number 5. In the following diagram, triangle ABC has been drawn and side BC has been extended to point D. Point E has been located such that auxiliary segment CE is parallel to AB. Ooh, let me lay all this out for you. Okay, I got some random triangle. It could be a right triangle, it could be an obtuse triangle, an acute triangle, it could be an equilateral triangle, it doesn't matter. And basically what I'm going to do is I'm going to take one of the 3 sides, and it doesn't matter which, but I've taken side BC, and I'm just going to extend it. I'm going to make it longer out to point D. How much longer? Doesn't matter at all. I just got to make it a little bit longer. And then what I'm going to do is I'm going to take and I'm going to draw a line segment from this point C up to point E, and I'm going to just make it so that that line segment is parallel to this line segment. All right, so let's start with a very basic question. Letter A. What allows us to draw segment CE such that it is parallel to segment AB? What allows us to do that? Allows us to do that? Well, honestly, it goes all the way back to something that we did in Unit 1. That's what's called Euclid's parallel postulate. All right, and what Euclid's parallel postulate says is if I've got a line, you know, like AB, and I've got a point not on the line, like C, then there is one line, and only one line, that can be drawn through it that is parallel to this and passes through that point. So I have permission at any point to draw a line parallel through a point that doesn't lie on that line. Okay, Euclid's parallel postulate. All right, we've actually used it a fair amount already in this course. Now, letter B, I'll move this up a little bit, says given that AB is parallel to CE, what angle must be equal to the measure of angle 1, and why? So think about this for a minute. What angle has to be equal to the measure of angle 1, and why? Well, I'm hoping that you said that it's got to be 4, angle 4. Now why? Well, because they are alternate interior angles. Now make sure you can really picture that. All right, this is incredibly important. All they are is the angle of that Z, right? In this case, it looks more like an N than a Z. But those 2 angles are alternate interior angles, right? These are parallel lines being cut by transversal AC, and 1 and 4 are alternate interior angles. I have got way too much going on this diagram right now. All right, great. Cleaned it up a little bit. So, angle 1 is congruent to angle 4. Let's at least mark that. Now, letter C. Given that AB is parallel to CD, what angle must be equal to the measure of angle 2? And why? Again, hopefully, I'm hoping you said angle 5. Now, why are angle 2 and angle 5 congruent? They're corresponding angles, right? Now again, this is a little bit tricky to see. You almost want to sort of mentally remove line segment AC, right? But if you remove line segment AC and you're just left with AB, right? So this is B, this is A, this is C, and this is E, then here's 2 and here's 5. And they correspond with each other, so they're corresponding angles. So in the case of letter B, we had alternate interior angles, and in the case of letter C, we had corresponding angles. Okay? So finally, letter D says, explain why we can now conclude that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 must be equal to 180. In other words, why can we really do it now? We can say that the sum of the three angles of a triangle is 180 degrees. Well, let's make the argument. Well, what we can definitely say is that the measure of angle 3 plus the measure of angle 4 plus the measure of angle 5 is 180 degrees. And that's because they form a straight angle. Right? Should be very obvious. 3, 4, and 5 form this 180 degree or straight angle. But now we know, right? We know that 4 was equal to 1, and we know that 5 was equal to 2. So, using the amazingly obvious property of substitution, we can now substitute 1 for 4. We can substitute 1 for 4 and 2 for 5, and we can say the measure of angle 3 plus the measure of angle 1 plus the measure of angle 2 is equal to 180 by substitution. Of course, I might not have them in the right order, but I could use the commutative and associative properties of addition to swing them around into 1 plus 2 plus 3 is 180. And it's really kind of cool. Again, it goes back, this proof of the sum of the angles is 180, really goes back to a couple different important ideas. Important idea number one is the fact that you've got Euclid's parallel postulate, which just allows us to extend that line segment and make it parallel to this one. And we could do it from any one of these given sides. All right, but as soon as we do that, and as soon as we extend side length BC out there, we create these two angles, right? And let me again do them in red, because I think that'll help. We create this angle, 4, which is congruent to 1, right? And, again, maybe even another color. And we create this angle 5, which is congruent to 2. And now, because 3, 4, and 5 must add up to 180 degrees, 1, 2, and 3 must add up to 180 degrees. And it's really kind of cool. You may have even done some things in middle school where you took a triangle and you cut it out and you rotated it and put it here and then translated it and put it there, because that's really what's going on here. This is a rotation of this triangle, so it ends up there. And then really, out here, which I lost, this triangle over here is really this one that's kind of been just translated over. All right? The sum of the three angles of a triangle is equal to 180 degrees. Ooh, this is one messy board. Let me step out of the way, though, so that you can write down anything you need to. Maybe bring this up a bit, and then we'll wrap up the lesson. Okay, let's do it. So in the lesson today, we primarily wanted to review some terminology, like alternate interior angles and corresponding angles. And we also wanted to review the fact that those types of angles are congruent. We saw a few other, though, important results today. One of them was that angles that are on the same side of the transversal, created by parallel lines, and their interior are supplementary. I almost said complementary, but they add up to 180 degrees. We also saw a fact that you likely already knew, which was that the sum of all three angles of any triangle will be 180 degrees. And we'll use that fact quite a bit from now on. Now that we've proved it, we can use it. That's the general way this course will go. Once we've proven an idea, we can use it then as a fact for the rest of the course, all right? If we haven't proven something, it's kind of dubious if we're using it. Okay, but more on that later. For now, I want to thank you for joining me for another Common Core geometry lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.